Welcome back to AI, from zero to researcher. Over the last 6 episodes, we built a complete toolkit. Models as parameterized functions, neural networks that learn their own features, gradients that tell parameters which way to move, evaluation that keeps us honest, and optimization tricks that make training actually work. Today, episode 7, we point all of that machinery at a new kind of problem: sequences. Text, speech, time series, anything where order matters. And we are going to watch the dominant approach before transformers rise, succeed, and then hit a wall so hard that an entirely new idea had to be invented. If the embeddings from episode 3 or the gradient issues from episode 4 feel fuzzy, revisit those before continuing. Both ideas show up here in a big way. Translate this. The cat sat on the mat because it was tired. What does it refer to? You needed to look back 7 words. Now imagine doing that through a bottleneck that can only hold one fixed size vector. That is the problem recurrent neural networks had. And it is not a minor inconvenience. It is a fundamental architectural limitation that gets worse with every word you add to the sentence. Today, we are going to build the system that had this problem, watch it work on short sequences, watch it fail on long ones, and understand exactly why. Because here is a research habit worth burning into your brain. Study the failure mode that motivated an innovation before studying the innovation itself. The innovation, attention, comes next episode. Today is about the failure. Before any sequence model can do anything, we need to turn text into numbers. This happens in 2 steps. First, tokenization. The input is split into discrete units called tokens. Depending on the system, a token might be a whole word, a subword piece, or even a single character. The point is, we go from a string of text to a list of symbols the model can index. Second, embedding. Each token is mapped to a dense vector of real numbers, its embedding. If you remember episode 3, this is the same idea we saw there. Representing discrete objects as points in a continuous vector space. A word is no longer just a symbol. It is a location in a learned space where similar words end up near each other. The model does not know these relationships at the start. The embeddings are parameters. They are learned during training, just like every other weight in the network. The key difference from earlier episodes is that now we have a sequence of these vectors, and the order matters. Dog bites man and man bites dog use the same words but mean very different things. How do we process a sequence while respecting that order? The idea behind recurrent neural networks is elegant. Process the sequence one token at a time and carry forward a hidden state that summarizes everything seen so far. At time step 1, the cell takes the first token embedding and an initial hidden state, usually zeros. It produces a new hidden state. At time step 2, it takes the second token embedding and that updated hidden state. And so on, one step at a time, threading a summary through the entire sequence. The same set of parameters is shared across every time step. This is parameter sharing. The model applies the same transformation at every position. That is what makes it a recurrent network, the same function applied recurrently. This design handles variable length sequences naturally. A sentence with 5 words gets 5 steps. A sentence with 500 words gets 500 steps. Same parameters, different number of applications. The math of a vanilla RNN is almost disappointingly simple. At each time step t, the new hidden state h sub t is computed by combining the previous hidden state h sub t minus 1 with the current input x sub t through learned weight matrices, adding a bias and passing the result through a nonlinearity like tan A. That is the entire model. One equation applied repeatedly. But this simplicity hides a serious problem. The hidden state h sub t is a fixed size vector, say 256 or 512 dimensions. Every piece of information about the sequence so far must be compressed into that vector. Early tokens get overwritten by later ones. The model has no choice. Same vector, finite capacity. Here is the math that makes this precise. At each step, the hidden state is multiplied by the weight matrix WH inside the tange. If the effective gain of that multiplication is less than 1, say 0.9, then after 50 steps, the signal from the first token is scaled by 0.9 to the power of 50, which is about 0.05. The information does not just fade metaphorically, it fades exponentially. This is the vanishing gradient problem from episode 4, now playing out across time steps instead of layers. LSTMs, long short-term memory networks, were designed to help. They had a separate cell state and 3 gating mechanisms. A forget gate that decides what old information to discard. An input gate that decides what new information to store. And an output gate that decides what to expose as the hidden state. GRUs, gated recurrent units, are a simpler variant with 2 gates instead of 3. These gated architectures improve things significantly. They could model longer dependencies and were the workhorse of NLP from roughly 2014 to 2017. Machine translation, speech recognition, text generation, LSTMs were everywhere. But the fundamental bottleneck did not disappear. It just got pushed further. The bottleneck shows up most clearly in sequence-to-sequence models, the encoder-decoder architecture used for tasks like machine translation. The encoder reads the entire input sentence, 1 token at a time, and produces a final hidden state. That single vector, the context vector, is supposed to contain everything the decoder needs to generate the output sentence. For short sentences, this works. For long sentences, it breaks. 20 words of meaning crammed into 500 numbers. Important details from the beginning of the sentence are faded or gone by the time encoding finishes. And there is a second problem, parallelism. Because each step depends on the previous hidden state, you cannot process multiple tokens at the same time. Step 5 needs the output of step 4, which needs step 3, and so on. On modern GPUs designed for massive parallel computation, this sequential dependency is a training speed bottleneck. This is the wall. Fixed capacity hidden states lose information over long sequences. Sequential processing wastes parallel hardware. These two problems together are why the field needed something fundamentally different. That something is attention, but we are saving it for episode 8. First, let's see the failure in code. Let's build a simple RNN and watch it succeed on short sequences, then fail on long ones. The task is deliberately simple. Look at the first element of a sequence and report it at the end. The only challenge is remembering across distance. We will use PyTorch, the same framework we introduced in episode 4, so we can use Autograd for training instead of computing gradients by hand. But we will write the RNN forward pass ourselves so you can see exactly what happens at each time step. Look at that contrast. On short sequences of length 5, the RNN learns the task well, 98% accuracy. On sequences of length 50, it barely beats random guessing. The task is identical. The only difference is distance. The information the model needs, the first element, has to survive 50 time steps instead of 5. Notice, the training code itself is clean. Autograd handles the backward pass through all 50 time steps automatically. The problem is not that we cannot compute gradients. The problem is that the gradients themselves vanish over long chains, just as we showed in episode 4's vanishing gradient preview. The optimizer receives near zero signal for the early time steps and cannot learn from them. Let's make the failure more precise. We will test the same architecture at different sequence lengths and watch accuracy degrade. There it is, a clean degradation curve. The model does not suddenly break, it fades. As the sequence gets longer, the memory of the first token weakens until it is indistinguishable from noise. This is the vanishing information problem in action, and it is exactly the issue that Episode 4's vanishing gradients warned us about, now playing out across sequence length instead of network depth. This is why researchers in the mid-2010s were stuck. LSTMs helped push the curve further out, maybe to length 100 or 200 in practice, but the shape of the curve was the same. Eventually, distance wins. The fixed-size hidden state cannot hold everything. The question that changed the field: what if the model did not have to compress everything into one vector? What if, at each output step, it could look back at every input position and decide what was relevant right now? That is attention. Episode 8. Let's compress. Tokenization breaks text into discrete units. Embeddings map those units to learned vectors, the same idea from Episode 3 now applied to sequences. RNNs process tokens one at a time, threading a hidden state forward. That hidden state is a fixed-size summary of everything seen so far, and that is both the strength and the fatal limitation. LSTMs and GRUs add gates to control information flow, extending the effective memory. But the bottleneck remains, a fixed capacity vector carrying all context and sequential processing that prevents parallelism. We saw this in code. Short sequences, the RNN learns easily. Long sequences, accuracy drops to chance. The information from early tokens fades with distance. This is the problem that attention was designed to solve. Next episode, we replace the bottleneck with a mechanism that lets the model look back at every position in the input and dynamically choose what matters. The math turns out to be a weighted sum, something we have seen since Episode 2, but the weights are computed from the data itself. That is attention, and it is the single most important idea in modern AI. Here is a question to sit with until then. If the RNN's problem is that it compresses everything into one vector, what is the minimum change you would make to fix it? Not a redesign from scratch, just the smallest modification that removes the bottleneck. Think about that. The answer is surprisingly elegant, and it is exactly what Bottleneck and colleagues proposed in 2014. See you in Episode 8.